Module 3, Chapter 6, Entropy. In the first law of thermodynamics, we found the property of energy and conservation of energy. In the second law, we leads to define a new property called entropy. For defining a entropy, we required a second law of thermodynamics. We required a second law of thermodynamics for defining the entropy. Second law deals with a source and sink. The source will be there. A sink will be there. In between, heat engine, refrigerator or heat pump is provided. Q1, Q2, T1, T2. A heat engine, a work output can be obtained. W is equal to Q1 minus Q2. This is the second law of thermodynamics. Second law of thermodynamics. Sometimes the entropy also referred as a second law of thermodynamics. Sometimes entropy is also referred as a second law of thermodynamics. Referred as a second law of thermodynamics. Now, definition of the entropy is definition of entropy. Entropy can be considered to be a measure of disorder. Measure of disorder we refer as a entropy. Measure of disorder we refer as a entropy. Measure of disorder we refer as a entropy here. Entropy Entropy can be considered as a measure of disorder. That means it is an abstract property. It is very difficult to express the entropy, especially the entropy. Okay. Now, for understanding purpose, I will consider a temperature entropy diagram, a TS diagram, temperature entropy diagram, state 1 and state 2. This is S1, this is S2, S1 and S2. Now, with respect to concept of entropy, as the temperature decreases, now see here, the temperature is decreases from state 1 to state 2. Then what happens? The entropy increases from 1 to 2. The entropy increases. That means when temperature decreases, entropy increases. Entropy increases. Now see here, from state 1 to state 2, the temperature decreases. As a result, the entropy increases. Now state 1 and state 2 refers what? It is a movement of piston inside the cylinder. At the beginning, the piston is here, but as the heat is applied, the piston moves here. As a result, the molecular will be move here. Molecules move here. There is a larger space. As the larger space indicate the increase in entropy. When the piston moves from 1 to 2. When the piston moves from 2 to 1, what happened? It compresses. When it compresses, what happened? The entropy will be decreases. Entropy decreases, the temperature increases. Now see the concept. This is a piston arrangement. A heating is applied. The piston movement occurs from state 1 to state 2. Here, the temperature drop occurs. As the temperature drop occurs, there is an increase in the entropy. There is an increase. 1 to 2, the entropy is increased. Now, during the compression, what happened? During the compression, the entropy will be decreases. Entropy decreases, but temperature increases. This property we call as entropy. Now, entropy is denoted by ds, delta S or ds, or sometime I will refer as delta S also. This is a delta. This is also delta, representation of delta S is equal to delta Q by T or Q by T, Q by T, Q by T. That means heat with respect to temperature we call as an entropy. Heat with respect to temperature we call as a entropy. Heat with respect to temperature we referred as entropy here. Entropy. Entropy can be considered as a measure of disorder. Disorder is nothing but the molecule movement. We refer as a disorder, not in order. We call it as a disorder. Or let us consider temperature and entropy diagram. Now piston movement from the state 1 to state 2, the temperature drop occurs. As the temperature drop occurs, the molecule move freely with increase in space, which indicate the entropy increases. When temperature drop occurs, the entropy increases. When it is compressors, what happened? The entropy decreases, the temperature increases. Temperature increases. That means entropy is depends upon heat and temperature. Depends upon heat and temperature. This is the delta S. Delta S is nothing but Q divided by T or delta T divided by delta Q divided by T. And unit is kilojoule per Kelvin. If it is divided with mass, we have to consider as kilojoule per kg into Kelvin. If it is divided by mass. Otherwise, the unit will be kilojoule per Kelvin. Kilojoule per Kelvin. Kilojoule per Kelvin. Because this is the kilojoule and T is expressed in terms of Kelvin. Therefore, it becomes kilojoule per Kelvin. If it is divided by mass, therefore we have to consider kilojoule per kg into Kelvin. Now, first concept is Clausius theorem. Clausius theorem. Here we are considering a smooth closed curve. Considering a smooth closed curve. The PV diagram. PV diagram, circular curve. Circular curve. A smooth curve. A, B, C, D. A, B, C, D. Now divide this curve into number of strips. We are dividing into number of strips here. Number of strips we are going to divide. Divide into number of strips. And close to successive reversible adiabatic process by means of a isothermal process. Now we have to close it with the help of isothermal process in this way. Isothermal process. In this form we have to close it. Isothermal process. Isothermal process. That means it has to be in the form of this way. One, two, three, four. These two we referred as an adiabatic, and these two we referred as isothermal. We have dividing into terms of adiabatic and isothermal. Adiabatic and isothermal. These vertical lines we referred as an adiabatic lines. Reverse adiabatic lines. Reverse adiabatic lines. And these inclined lines we referred as an isothermal lines. This is also isothermal lines. Isothermal lines. Isothermal. Reversible isothermal. Reversible isothermal. Reversible isothermal. Now let us consider a strip P, Q, R, S. One more strip U, V, W, X. Consider two strips. Here PQ, in isothermal process, the heat is added, and in isothermal process 1,4 the heat rejection occurs, and during adiabatic process there is no heat interaction occurs. During 2,3 the heat addition occurs, during 1,4 the heat rejection occurs, and these are two adiabatic process where is no interaction of heat. Similarly, here delta Q1 heat interaction occurs, here delta Q2 heat rejection occurs. Similarly, the second strip, delta Q3 heat addition occurs, here delta Q4 heat rejection occurs. Heat rejection occurs. This is the original cycle. This is the original cycle. Now let us first Carnot formed is PQRS, where delta Q1 heat added, delta Q heat rejection. Next strip is WV PQRS I have written. No, it is UVWX. It is UVWX. Heat addition occurs, heat rejection occurs. We are considering only two strips. Now, with respect to strip 1, for strip 1 or PQRS through the Carnot cycle, by using entropy concept, we have to write as delta Q1 divided by T. Here temperatures T1, T2, T3, T4, temperatures will be there. Temperature delta Q1 divided by T in terms of entropy we have to express, is equal to heat addition is equal to heat rejection, delta Q2 divided by T2. Now, as we know that heat addition is considered as a positive and heat rejection is considered as a negative here. Therefore, delta Q1 divided by T is equal to minus delta Q2 divided by T2. Delta Q1 divided by T1 is equal to minus delta Q2 divided by T2. Bring this side, delta Q1 divided by T1 plus delta Q2 divided by T2. Minus and indicate the heat rejection. If a body is there, heat addition we will consider as a positive, heat rejection we will consider as a negative. Therefore, negative sign. Bring this direction, it becomes positive, Q2, delta Q2 divided by T2. This is the with respect to strip 1. Now we are solving for with respect to strip 2. Strip 2. Or UVWX. Here it becomes delta Q2, the strip 2, delta Q3 divided by T3. Delta Q3 divided by T3 is equal to delta Q4 divided by T4 with respect to strip 2. In terms of entropy. Here the heat rejection is considered as negative. Therefore, write in this way. Delta Q3 divided by T3 minus delta Q4 divided by T4. Bring this direction. Delta Q3 divided by T3 plus delta Q4 divided by T4. 0. Now, if you consider the strip third, then what happened? The equation will be you consider strip third, then the equation becomes delta q5 divided by t5 plus delta q6 divided by t6 is equal to 0, and so on. If you consider n number of strips, the n number of equation will be there. Therefore, it can be written as in this form, delta q1 divided by t1 plus delta q2 divided by t2 plus delta q3 divided by t3 plus delta q4 divided by t4 and so on equal to 0, equal to 0, equal to 0, equal to 0. Now, this can be written in generalized form, integration with a reversible cycle delta q divided by t is equal to 0, equal to 0, where r indicate a reversible process, where r indicate a reversible process, r indicate a reversible process. This is the general equation with respect to Clausius equation, which is equal to 0. The reversible is nothing but if you start from state 1 to state 2, 1 to 2, again it has to reach to the 2 to 1. 2 to 1 we call as a reversible process. Irreversible is moves from 1 to 2, it doesn't cover from the 2 to 1. We call it irreversible process. The reversible process is nothing but here, that means it should be a 0. It should be a 0. Consider example of reversible is water and ice. Water and ice. You can go for converting water into ice into water because it's a reversible process. Reversible process. Okay, this is the expression with respect to Clausius theorem. Integration of delta q divided by t is equal to 0, or it also can be written as delta integration is equal to q divided by t is equal to 0 for the reversible process. Reversible process. This is called as a Clausius theorem. Clausius theorem. Clausius theorem. Next is entropy, a property of a system. Entropy, whether it is a point function or path function, we need to derive. Entropy, a property of a system. Property of the system. Property of a system. Now see here, there are three concepts exist. This we referred as a system. Surrounding. Around this one we call as a universe. System, surrounding and universe. Now entropy, a property of system. Entropy, a property of a system. We are discussing about the entropy as a property of system. That means we have to arrive whether it is a path function or a point function. Path function or a point function. Consider a reversible process 1 to 2, A, reversible, 2 to 1, reversible, B, reversible. Again one more path I am going to consider from 2 to 1, C, reversible. That means whether this property depends upon the path or a point, we are going to define here. We are going to define. Consider a reversible cycle. A reversible cycle 1, A, 2, B and 1 from the Clausius theorem. Clausius theorem. Clausius theorem. That means integration of delta q divided by t is equal to 0. This is the Clausius theorem. Clausius theorem. Now with referring this Clausius theorem, you have to write integration 1a to 2a delta q divided by t, moving from the path 1a and 2. Next, from moving from the path 2b and 1, plus integration 2a to 1. 2b to 1 1b. See here, 1a to 2a delta q by divided by t, plus from the path b 2b integration of 1b delta q divided by t is equal to 0. This is considered as equation 1. Again, instead of moving to the path b, if it is moved to the path c, then what happens? Again, for the reversible cycle, 1a to c1, we can write integration of 1a to a delta q divided by t, plus integration of 2c 1c delta q divided by t is equal to 0. Equation 2. Now subtracting equation 2 minus 1 from 1, we get, subtract it, write this equation, 1a to a delta q divided by t, plus 2c 1c delta q divided by t, minus first equation, minus 1a to a delta q divided by t, minus this plus becomes what? Again minus integration 2b 1b delta q divided by t is equal to 0. Here this and this get cancelled, and it can be written as integration of 2c 1c delta q divided by t is equal to, minus integration of 2b 1b delta q divided by t is equal to 0. Now move this one in this direction. Integration of 2c 1c delta q divided by t is equal to 2b 1b delta q divided by t. That means the quantity delta q by t is same for both the path. The quantity delta q by t is same for both the path b and c, and hence it doesn't depend upon the path. This path delta q by t will be same, and hence it doesn't depend upon the path, but depends upon the states. Thus it is a point function. That means delta q by t remains same. The path, it doesn't depend upon path, but it depends upon the states. States are nothing but these points. It depends upon the points. Therefore, it is a point function. Thus, it is a point function. Thus, it is a point function. Further, delta Q by T is written as entropy ds or delta S Q by T. Q by T. Delta indicate what? If it is a movement occurs, if there is a change occur, therefore we have to consider as S2 minus S1 is equal to integration of 1 to 2 delta Q by T. This is also formula we need to use while solving the problem. Delta Q by T we referred as a ds or delta S, which is also called as Q by T. With delta indicate what? The change in delta indicate the change in entropy. Change in entropy is written as S2 minus S1. Integration of 1 to 2 delta Q by T. This is about the entropy, a property of a system. That means entropy, a property of system, we need to define whether it is a path function or a point function. Whether it depends upon the path, whether it depends upon the point. Because it doesn't depend upon the path because delta Q by T, delta Q by T, delta Q by T. It depends upon only the points. It depends only upon the points. Depends only on the points. This is about the entropy property of a system. This is the Clausius equation. Delta Q by T is equal to 0. 0. 0 indicate irreversible. 0 indicate reversible. Now, by using this Clausius theorem, we have to define entropy whether it is a path function or a point function. Whether it is a path function or point function. With this derivation, we came to know that it is a point function. It is a point function. The next concept is two reversible adiabatic process. The two reversible adiabatic process okay. Now, next concept is two reversible.
Sir, your screen is lagging, sir.
It is lagging.
Yes, sir.
No. Now it is okay.
Now is also like
Okay, or still it is lagging.
still it is lagging, sir. You can write it. We can just note it down the.
Okay, it is a theory part.
Okay. Sir.
Now, two reversible adiabatic process cannot intersect each other. It is a adiabatic process. The two reversible adiabatic path cannot intersect each other. Now, with respect to Carnot, we know that there are two isothermal process and two adiabatic path. A, B, C, D. These are reversible isothermal, and these are reversible adiabatic. Reversible adiabatic and reversible isothermal by using this Carnot engine PV diagram. PV diagram. This is also PV diagram. Now what happened here? One isothermal and two adiabatic path. One isothermal and two adiabatic path here. Reversible isothermal, and these two are adiabatic path. Reversible adiabatic path. Here the cycle consisting of three processes. Three processes. Now this is a Carnot engine, Carnot cycle. Carnot cycle. It consisting of a four processes, two isothermal and two adiabatic. During isothermal, the Q amount of heat is added. During C and D process, the heat rejection occurs. During the adiabatic process, neither be heat is added, nor be rejected. Now, two reversible adiabatic paths cannot intersect each other. This is the condition. That means the two reversible adiabatic paths cannot intersect each other. Now, here what happens? The heat addition occurs and performs some amount of work. Then there is no heat rejection. Then this violates Kelvin-Planck statement. If you consider the practical point of view, it's a heat engine, source T2, Q1 minus Q2. This is the Q1, Q2. That means the heat is taken from the source. In the engine, the work is performed and heat is rejected to the sink. This is the basic concept. But here what happens? If a path, a isothermal single path and two adiabatic paths are connected, then what happened? Whatever the heat extracted, it is getting converted into work, which is impossible. Thus, it violates the Kelvin-Planck statement. This is about the two reversible adiabatic path cannot intersect each other. The two reversible adiabatic path cannot intersect each other. That means if two adiabatic paths are connected, if there is no isothermal process, then what happens? There is no heat rejection. It indicates what? Q1 amount of heat is added to engine and 100% of work is done, which is impossible, which violates the Kelvin-Planck statement. This is about the two reversible adiabatic path cannot intersect each other. Thus, it violates Kelvin-Planck statement. It violates the Kelvin-Planck statement. The next concept is, still it is lagging?
Yes, sir.
Just wait. Next concept is Carnot cycle on temperature, entropy diagram. Carnot cycle on temperature, entropy diagram. entropy diagram, temperature entropy diagram. Temperature entropy diagram. This is a PV diagram. Carnot cycle. One, two, three, four. 1 to 2, the heat addition. 3, 4, heat rejection. Now, with respect to entropy diagram, you have to represent in this form ES diagram. ES diagram. This is the representation of ES diagram with respect to Carnot cycle. A, B, C, D, T1, T2, Q1, Q2. Here heat addition occurs. This is the adiabatic. CD are adiabatic, BC is adiabatic, AB is isothermal, CD is isothermal. CD is isothermal. Let us consider this E, F. Temperature and entropy diagram. Temperature and entropy diagram. Temperature and entropy diagram. Now, the heat addition during isothermal process or isothermal expansion AB. Here the expansion occurs, here the compression occurs. Can be written as in terms of entropy we have to write. We know that entropy delta S is nothing but Q divided by T. Delta S is equal to Q divided by, or ds is equal to delta Q by T. Delta Q by T. We have to write in terms of Q with respect to expansion. See how to write that one. Q1 is equal to area. Q1 is equal to area ABFE. ABFE. Area Q1 can be written as T1 into SB minus SA. SB minus SA. It is similar to here. Q is equal to delta S into T. So delta S is written as in terms of expansion. First we have to take B, SB minus SA into T. It is written here. It is written in terms of entropy here. Heat addition during isothermal expansion AB. Q1 is equal to area ABEF is equal to T1 into delta S. Delta S is nothing but expansion. If it is expansion, first we have to take SB minus SA. SB minus SA. SB minus SA. During compression, we have to take SC minus SD. Now, heat rejection. Heat addition occurs. Heat rejection during isothermal compression. Isothermal compression CD. Here the CD, the heat rejection occur. It is written as Q2 is equal to area DCFE. This is the area DCFE, or T2 into SC minus SD. SC minus SD. If it is a compression, the backside of arrow we have to take. If it is expansion, the pointer we have to take. Consider the equation 1 and 2. Equation 1, equation 2. Now, here it can be written as SB can be written as here. SB can be written as SC, SC and SA can be written as SD. SD. SA can be written as SD here. SA can be written as SD. Now, the net work output, the work done, the net work done is written as W is equal to Q1 minus Q2, Q1 minus Q2. Now Q1 is T1 SB minus SA minus T2 T2. Now in place of SC write SB, in place of SD write SA, SA. Take common SB minus SA, SB minus SA common into T1 minus T2, T1 minus T2, T1 minus T2. This is the work done. We know the efficiency of Carnot engine. From the efficiency of Carnot engine, cycle efficiency is neta is equal to net work done divided by heat supplied. Heat supplied. W divided by Q1. W divided by Q1. The W value is given here. Substitute SB minus SA, T1 minus T2 divided by Q1 is the Q1 value. T1 SB minus SA. Here these and these get cancelled. T1 minus T2 divided by T1. T1 divided by T1 minus T2 divided by T1 get cancelled. 1 minus T2 divided by T1. Now Carnot cycle, by using entropy, the equation is neta is equal to 1 minus T2 divided by T1. T2 divided by T1. In the fifth chapter, we have derived by using pressure and volume. In this chapter, we have derived through the entropy. Through the entropy, neta is equal to 1 minus T2 divided by T1. In the last chapter, we have derived pressure by volume. Through the pressure and volume, we have defined neta is equal to 1 minus T2 by T1. Now, through the entropy, we have derived neta is equal to 1 minus T2 minus T1. T2 minus T1. This is the Carnot cycle on temperature entropy diagram. In the fifth module, we have completed Carnot cycle based upon pressure and volume diagram. Here, temperature and entropy diagram. Temperature, entropy, we have to arrive neta is equal to 1 minus T2 divided by T1. T2 divided by T1. T2 divided by T1. T2 divided by T1. Next concept. Inequality in Clausius theorem. 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 Heat source T1, heat engine HE, temperature, heat source temperature, and heat engine Q2, sink, heat sink, T2, work is Q1 minus Q2. Work is Q1 minus Q2. Now we know that the efficiency of Carnot engine, Carnot cycle with respect to entropy neta is equal to 1 minus T2 divided by T1. Now T2 can be replaced by 1 minus delta Q2 divided by delta Q1. 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 The sound is audible?
Yes, sir.
Now, one more concept with respect to Carnot theorem is that neta reversible always greater than equal to neta irreversible. Neta reversible always greater than equal to neta irreversible. Based on this concept, we have to arrive whether the cycle is reversible, reversible, irreversible and impossible. Now here neta is equal to neta r greater than equal to neta irreversible. Now neta r is written as 1 minus delta q2 divided by delta q1, delta q2 divided by q1 r greater than equal to 1 minus delta q2 divided by delta q1 for irreversible I, for the I, for I. Now this can be replaced with the temperature. You can replace with the temperature here. 1 minus T2 Q1, it is Q1. T2 divided by T1 reversible greater than equal to 1 minus Q2 divided by Q1 delta Q1 irreversible. Minus 1 get cancelled, minus get cancelled. T2 divided by T1 greater than equal to delta Q2 divided by delta Q1. Delta Q1. Delta Q2 divided by delta Q1. Now we have to bring in the form of entropy. Now see here how to bring that in the form of entropy. Move delta Q1 here. Delta Q1 divided by T1, while moving, this greater sign becomes less than equal to delta Q2 divided by T2. Delta Q2 divided by T2. While moving, the greater sign becomes delta less than delta Q2 divided by delta T2, because we have to express in terms of entropy. Further, bring this direction. Delta Q1 divided by T minus delta Q2 divided by T2 less than equal to 0. Less than equal to 0. Now we know that heat rejection is considered as a negative. Heat rejection we will consider as a negative. The heat addition is positive. Heat rejection is negative. Therefore, this is the heat rejection part. Delta Q1 divided by T1 minus delta Q2 divided by T2 less than equal to 0. Further, it can be written as delta Q1 by T1 plus delta Q2 divided by T2 less than equal to 0. Less than equal to 0. Now, in the form of generalized equation, it can be written as integration of delta Q divided by T is less than equal to 0. Less than equal to 0. Now see here, there is a inequality of Clausius theorem. For reversible process or a cycle, we know that integration of delta Q divided by T is equal to 0. For irreversible process, irreversible process, integration of delta Q by T is less than 0. This is the less than equal to 0. This is an irreversible process. And for integration of delta Q divided by T greater than equal to or greater than equal to 0, we call as a not possible or impossible. We call as a impossible. The above equation A, this is A, we call as a Clausius inequality. If it is 0, we will call that as a reversible process. If it is less than 0, we will call it as an irreversible process. The process doesn't repeat. If it is greater than 0, we call it as an impossible process. We call it as an impossible process. This is about the inequality in Clausius theorem. Inequality in Clausius theorem. If it is delta Q divided by T is equal to 0, if the value obtained is 0, we call it as a reversible process. If it is less than 0 means in terms of negative value, then we call it as an irreversible process. If it is positive value, that means more than 0, maybe 1, 2, 3, we call it as impossible. If it is minus 0, minus 1, minus 2, minus 3, we call it as irreversible. If it is equal to 0, the process is reversible. That means conversion from water to ice, ice to water, it is possible. But in the irreversible, it is not possible. And if it is greater, it is impossible. It is impossible. Based on this one, we are solving the problem now. The first problem. Now see here, first problem, whether it is a reversible, irreversible or impossible. A heat engine absorbs 200 kilojoule per second of heat at 227 degrees Celsius. It is a heat engine. It is a heat engine. Okay. Heat engine. T1, HE, W, T2, Q1, Q2, Q1 minus Q2. It is a heat engine. Absorbs the heat at 227 degrees Celsius. T1 value is given. T1 is 227 degrees Celsius. Convert in terms of Kelvin. 227 plus 273. 500 Kelvin. It absorbs the heat from a source. Therefore, Q1 is equal to 200 kilojoule per second. And reject the heat at 27 degrees Celsius towards the sink. T2 is equal to 27 degrees Celsius. Convert in terms of Kelvin. 27 plus 273. 300 Kelvin. 300 Kelvin. There are three cases. There are three separate cases for heat rejection. Heat rejection cases. Case 1, 180. Now, according to Clausius, we know that integration of delta Q divided by T is equal to 0. By using this equation, how to write here? Q1 divided by T1 minus Q2 divided by T2. Now see here, we have to write Q1 divided by T1 minus Q2 divided by T2. Minus indicate heat rejection, because in terms of entropy we have to write entropy. Either you can consider delta Q1 divided by T1 minus delta Q2 divided by T2, one and same. Here delta Q1 is referred as Q and delta Q2 Q2. Now Q1 is, this is the Q1 value. Q1 value is 200. T1 is 500 minus Q2, case 1. Case 1, heat rejection. There are three cases, heat rejection. 180 divided by T2 300. 300. $200, 500 minus 180, 300. The value is minus 0.2. Now, if it is minus 0.2, then the process is reversible or irreversible? Anyone? If it is minus 0.2, if it is a minus sign indicate.
Irreversible.
Excellent. Now it is an irreversible process. It is an irreversible process. Minus sign indicate it is an irreversible process. Now let us go with the case 2. Integration of delta Q divided by T, Q1 minus T1 minus Q2 divided by T2. Now Q1 is known 200, T1 is 500. Now case 2, 120 divided by T2 is 300. Use the calculator. Use calculator. Now answer is 0. Now it is 0. What is the process? If it is 0, what is the process? Anyone?
Reversible.
It is reversible. It is reversible. Now case 3, integration delta Q divided by T, Q1 minus T1 minus Q2 divided by T2, 200 divided by 500 minus Q2 is 60 divided by T2 is 300. Now it is 0.2 plus 0.2. Now what is plus 0.2? We call as a impossible. This process doesn't exist. Impossible. Impossible. Okay, I will solve one more problem. ये थोड़ा ऑफ कर दो भाई थोड़ा. Now see here, a heat engine is supplied with a 278 kilojoule per second of heat, constant fixed temperature at 283 degrees Celsius, and heat rejection occurs at 5 degrees Celsius. The following results were received. Now see here, Q1 is given 278 kilojoule per second. Temperature T1 is given 283 degrees Celsius. 283 plus 273. 283 plus 273. 556 Kelvin. Heat rejection 5 degree. That means T2 is equal to 5 degrees Celsius. 5 plus 273. 278 Kelvin. 278 Kelvin. There are three cases. 208, 139, 70 kilojoule per second. Whether we have to find out, reversible, irreversible and impossible. Now case 1, integration of delta Q divided by T, Q1 T1 minus Q2 divided by T2. Q1 is 278 divided by T1 is 556 minus Q2 case 1. Case 1 208 divided by 278. The answer is minus 0.248. Irreversible process. Next question, second part, integration delta Q divided by T, Q1 divided by T1 minus Q2 divided by T2, 278 divided by 556 minus 139 divided by 278. Answer is 0. The process is reversible. Process is reversible. Third case, integration delta q divided by t, q1 minus t2, t1 minus q2 divided by t2, t2, 278 divided by 556 minus q2 is third case, 70 divided by 278. Answer is 0.248. Positive. Impossible. Impossible. Impossible cycle. Impossible cycle. This is with respect to Clausius theorem in terms of entropy. In terms of entropy. These are the problems. These are the problems.